All right, hello guys. As Matt said, I'm Lindsay, and I'm giving this presentation on what we've done using Python to span the gap between education, industry, research, and we've been doing this using a package called Simpang, which is something we've been developing in our group. And one thing to mention here is, although I'm the one giving this presentation, there's a great team of people that's behind this. And so there's Rowan, who you may have seen giving a lightning talk yesterday, and Gutney will be presenting later today. So the three audiences we want to be considering here are research, industry, and education. And so each of these groups needs access to a different level of detail when we're talking about a given concept. And so we're going to walk through that in a little detail here. So what we've got here is conceptually what each of these groups wants as tools to sort through some of these concepts and accomplish what they need to. So we'll start at the top. Got education here, and so what students need is they need some sort of tools that enable them to explore concepts. So we want to give them a couple parameters to play with, have that go into some sort of system, and then they get outputs. And so we want them to be able to rapidly explore concepts and ideas and get that input and have them be the ones driving the interaction. In terms of industry type problems, what we're working with here is you want to be able to wrap that up so that we've got some sort of function that solves their problem. It's got some input, it's got some knobs, and has data that they can work with in existing workflows. Then in research applications, we want exposure to the details. So you start with some sort of question, and then we want to try and sort through these details and develop a methodology that is new and adds something to the field. And so I'm hoping to get a PhD out of that. So I know it's a diverse group here, and so the brief overview of geophysics is we've got a source. This source inputs energy into the subsurface. It generates responses, and we measure those responses somewhere on the surface usually, and we try and use that to infer what's going on underground. And so that step of going back to what's going on underground is the inverse problem. So we want to take our data and solve for what the Earth model is. The general workflow here, we've got quite a number of moving pieces. So we start out at the top. We've got the inputs. So we've got our data. We have the governing equations. And then we've got some sort of assumptions, maybe some geologic knowledge about the area. Then we've got the inversion implementation. And so there's two pieces you need there. We need to be able to forward simulate. So given a model, you need to be able to predict what your data look like. And then we have the inversion framework, where now we want to perform an optimization to find out what that model is. As I said, this is an iterative process. So you get some sort of model out of your inversion. Sometimes it makes sense, sometimes it doesn't. You go back, you reevaluate your assumptions, and try it again. So with all of these moving pieces, you need to be organized so that you can make productive progress as you sort through these problems. And so what we've been doing with Simpang is developing a framework which allows us to tackle these problems. So we've started by looking at a whole suite of problems in geophysics, from like EM, flow, seismic, and we've boiled down what they have in common. And that's what we've done here with this framework. So we've got the forward problem, where we've got the physics and the survey. So we set up sources and receivers. We can then forward simulate what those data look like. Those simulation tools are captured in the mesh. And then we perform some sort of inversion using an optimization in the rest of the framework. So one thing that's been really important when we codify this is that it is a modular framework. And so that allows you to keep all of these pieces in perspective, but then dive into the details when you need to. And of course, testing, again, moving pieces, they have to be tested. In the open, this is huge because it enables different types of conversations and different audiences to be brought on board. So here, this is just a screenshot. So we've codified this, available on GitHub. We're still a young package, but moving along. So now what we're going to do is walk through an example with each of these audiences. So we'll start with research, which is where I'm most heavily involved. And the problem I want to introduce you guys is to well casing. And so I've been looking at modeling electromagnetics in settings with well casing. And this is a weird problem because well casing is highly conductive. It's steel. You put it in when you drill a well. It's very long and it's very thin. And so when you talk about something that's that conductive compared to the surrounding rock, it has a really big impact on your signal. But that's not actually the thing we're interested in. We drilled the well, we know where the steel casing is, great. So we want to know what's going on in the geology surrounding there. And so in order to try and tackle this problem, we've been breaking it up into 2 steps. So we exploit symmetry in the first part, model the casing, and then use those fields as a source for the secondary problem, which includes the 3D geology. And so here, what makes this, there's a lot of details that make this interesting, but among them is the fact that we're dealing with different meshes. So in the first one, we make this cylindrically symmetric problem, and then we map it to a 3D problem from there. And then all of these operations, we want to consider the inverse problem. And so when doing that, you have to consider where your model matters. And so everything you do to your model along this process, you have to take a derivative of. And so when you do this primary-secondary formulation, what happens is you have model dependency on your right-hand side, which is weird. And so you have to be organized. And again, that comes back to this framework, is we need to know where to put all these pieces and where to focus our efforts. So the framework is an important part of that. Also, using base class inheritance. And so what we do is you enforce structure at a ground level, and then we can build upon this. And so each time we want to plug in a new piece, we can inherit from the work that we've already done. This also enables conversations to happen. And so talking about electromagnetics, it's a small field, but because we're building from a framework, I can talk to somebody in fluid flow or in seismic in this code and in this framework, and we can have a productive conversation. And them talking about flow, I can learn about electromagnetics in that conversation. All right, so moving on, we're going to just briefly touch on the industry applied side. And so in the context of the same physical problem, what they're looking at is how do you model casing and incorporate that model into the existing workflow and the 3D codes that they know and trust and like. And so what we want to do there is take this casing model, replace it with a simpler model, some sort of like equivalent source, and then they can use that in their existing 3D codes. And in order to do that, that's with packaging. So you package up the code, give people the knobs that they need, and the inputs and outputs that make sense to them. There's a few other things that are important there. I mean, we need to version, we need to be able to visualize geology, geophysics. You're dealing with 3D problems in fields. You need to be able to see what's going on. And then documentation and testing again. So moving on to education, this is something I'm extremely excited about, and I know quite a number of people in the group I'm with are thrilled here. So what is the problem that they're dealing with? So we've got students. I mean, when you're an expert in a field, you look at these equations and they're rich. You see fields and fluxes, and you see that, you've got a moving current that produces a magnetic field. These things are happening in 3D, and we have this brilliant, huge picture, and it's compressed down in these equations, and then we hand this to a student, and it doesn't really uncompress. And so what we want to do here is give them the resources to interact with these concepts and just play with them and have them start building some intuition. So how we've been trying to do this is lower the barriers to entry by just exposing the details that the students need and then giving them the tools to drive the interaction. And so I'm going to show you guys an app here, and this has been developed along with Rowan and 3-Point Science for my supervisor's undergraduate course. And so an important thing to know about this course is that it is a geophysics undergrad course, but it's for non-geophysicists. So these are students who are geologists, engineers, people who need to interact with geophysics, but don't necessarily need to know all the details of what's going on. They need to know the basics of what these methods are and what they might expect to get out of them. So let me just pull this guy over. See if that works. All right, so what this problem is this is the 3-loop electromagnetic problem. So we've got some sort of source and receiver here. So we've got, sorry, it's hard doing it on the screen. So we've got our source loop, which is this red guy. We're putting a current through there. And we've got a receiver loop that's going to pick up signals. And then we've got a target here. And so this target could be some sort of metal object we're trying to detect or something like that. So we try and put these problems in context. There's some cool surveys that have been done in Vancouver using this type of method, so we give students kind of this history there. But the problem here is we turn on a current here, and then a time-varying current produces a time-varying magnetic field. And so we have the students draw these field lines. All right, oh, that's a weird one. So let me try again. All right, so we draw these field lines, and they're 3D things. And so this is a hard concept to get, even having them draw it on a piece of paper, because we've got things coming in and out of the whiteboard and in and out of the page, and so you can't capture that with a pencil and a piece of paper. You can try hand signals, and sometimes that helps, but to have them capture that and them be the ones doing it, this is a really cool tool. So, okay, we get our primary field, and then that's a time-varying primary magnetic field. Now we've got some sort of loop down there, and so that flux is going through this loop. So that now produces a current in that loop, and then we get a secondary magnetic field produced from the loop. A little bit of a weird field line, but don't judge. All right, and so now you can see in 3 dimensions that we have all these field lines going everywhere, right? And then we can pick that up at the receiver, and so we see that we have a signal there. So now what happens, why is the signal 0 here? What's going on there? So let's draw the field lines. We turn on the primary field, all right? So we draw some field lines, maybe some bigger ones. All right, and we see that if you look at it, there's nothing going through that loop. There's no field lines going through the loop, so we're not coupled. So when you're actually right over top of it in that geometry, we're totally blind to it. And so this is a concept that you can only really get if you can see it in 3D. And so these are the types of tools. We're excited to be using this. This is the first time we'll use it in the course this year, this version of it. And so we're excited about the possibilities of putting these things in the hands of students. Cool, so I'll get back here. Another thing we're excited about with the notebook is working with students who are potentially more advanced or actually are in geophysics, is leveraging this package to have them do numerical simulations. So you don't have to be an expert in finite volume to see that div sigma grad in math looks like div sigma grad in code, and they can solve that. All right, so where are we headed? The base Simpang is up and available and is about 2 years old now. And we're continuing to add physics modules and geophysics packages, including like EM, MT, which you'll see if you stick around, flow, seismic. And so as we complete these packages or get them to a state that's digestible by others, we'll plug them into base Simpang. So just in summary, what we've got here is we've been working on building a box with building blocks. And so being able to play around with these, recombine, develop the methodologies in the research side, but also be able to package them up and distribute them so that people can use them in applied problems, and then have them be that system that allows students to just explore physics. This is something I'm really excited about, is on the horizon. So we've purchased a site called geosci.xyz, and what we want to do is use that to host these tools, but in the context of case histories. And so case histories being applied problems, for instance, like an environmental remediation problem. So if there's been some sort of spill, you want to detect that, characterize it, and remediate. That's a problem that involves a whole bunch of disciplines. And so students need to be able to be exposed and communicate between these disciplines. And so to put these types of tools in that context is something we're thrilled about. So if there are people in the audience that have case histories or examples or things like that that you think would be well suited for this, or you want to get involved, please get in touch, and we want to make that happen. So if you're interested in more, here's a few ways to get in touch with us. Thanks.